rejoined. So I'm Alistair Willis, Marketing Director for Geobear. Thanks to everyone for joining online. I can see there's quite a few people with us. With me is Dr. Mohamed Wehbi, our Technical Director for Geobear, and he's going to be presenting this webinar today regarding our solutions on the railways. So it's hopefully you'll find it interesting. It's quite technical. There's a chat box on the right hand side at the bottom, so if you've got any questions as we go through, you can type them in there and we'll come to them at the end. So I think without further ado, I'll hand straight over to Mohamed. It's all yours.
Okay, thank you very much, Alistair. So as Alistair kindly introduced me, I'm Mohamed Wehbi. I'm the Technical Director at Geobear. And in my previous life, I used to be a senior trackbed design engineer in Network Rail. And today I'll be talking to you about the use of geopolymer technology on the railway infrastructure. So first of all, who we are. So Geobear is a global leader in non-destructive solutions that would focus on treating foundation issues and subsidence issues. The company was originally established in Finland in the early 80s, and later on it was established in the UK in the early 90s. We've got multiple offices in the UK, and we've delivered more than 200,000 projects worldwide. We've got multiple branches worldwide, so in the US, Sweden, Finland, Poland, and China, in addition to what we already have here in the UK. We do work in various sectors, such as the highway sector, commercial, residential, energy, utilities, airports, and more recently on the railways. Before I go into talking about the use of this technology on the railway infrastructure, I always like to provide a brief introduction to what are geopolymers, so what this material is about. So what are geopolymers? Geopolymers are expandable resins that can be injected into the ground using special injection equipment for the purpose of void filling and soil stabilization. And I always like to play a video to show how the material looks like so you can better relate to it. So when it's injected in a liquid state, in a matter of seconds or minutes, it expands and solidifies. Depending on the type of geopolymer, it can expand up to 40 times its original volume, generating different amount of pressure. But obviously, depending on the application, you would choose the right type of polymer that would have a certain amount of expansion. Geopolymers also have excellent structural properties. So a geopolymer can have a compressive strength up to 7 MPa and a tensile strength up to 6 MPa. And as you can see here, it's not like concrete. Geopolymers are good in both tension and compression. So it's almost an isotropic material from that point of view. It can resist both forces almost at the same level. Also, geopolymers, yes, they've got really high compressive strength, but at the same time, their modulus of stiffness is somewhere between 10 MPa and 90 MPa, which is quite similar to what you get from natural soil and normal types of engineering fills. Also, geopolymers have excellent ability to resist fatigue damage under cyclic loading. So, like the type of loading you get from the railway is considered to be cyclic loading of a cyclic nature. So if you take a sample of a geopolymer and apply a similar loading from what you get from a railway environment, the geopolymers can last quite a substantial amount of time. In fact, they can last up to 120, 140 years under such type of loading. And if you compare that to like engineering fills, like type 1 engineering fill, the best type 1 engineering fill you can find, it could last, a type 1 should last you around 70 years. So a geopolymer will definitely outrun that life due to its ability to resist that type of damage. Also, other types of properties of geopolymers. Geopolymers can harden rapidly. So we're talking about they tend to harden and cure in matters of minutes or seconds. They are water-free solutions, so they do not require water to initiate the chemical reaction, so you're not going to be adding water to your system. Also, they're a super light material, they're 10 times lighter than conventional concrete and 5 times lighter than conventional grouting. So if you're using it, for example, to fill let's say a void on a structural element, you're not going to be adding any significant amount of dead load onto your structure. From a sustainability point of view, we've carried out extensive studies on to understand the environmental impact of our geopolymers by third-party consultancies. And what we've learned is that our geopolymers have a very stable molecular structure. They're hydrophobic, so they push away the water, and therefore they wouldn't contaminate or intermix with the soil, underground water and soil. You can even use after decommissioning, you can actually take the geopolymer out and you even use it as part of a landfill. So it's very safe, and it's not going to cause any contamination. Also, we've been doing a lot of carbon footprint studies on our products, and we've commissioned a study in 2018 by a third-party consultancy to understand the carbon footprint of our solution compared to conventional grouting. And what we've learned from that study is that our solutions would produce 46% less carbon footprint as opposed to typical grouting solutions. Now, this is the interesting bit. Now, what are the applications of geopolymers on the railways? Now, the first obvious application is the use of geopolymers to fill voids under slab tracks. Now, as some of you may know, that under slab tracks, the voids can develop due to dynamic loading. And this is especially the case when you have very soft underlying conditions combined with poor drainage. And eventually that would lead to structural cracking, poor track quality, and even track faults, and which can consequently result in speed restrictions, in imposing speed restrictions. What we can do, we can actually drill to the voids under the slab, which we can probably identify from the ground investigation, and create a 12mm diameter drilling hole, and insert our injection tube and start injecting the geopolymer inside the void to actually fill it, to fill the void. As the geopolymer gets into the void, it will start expanding and it will start pushing all the water away. We can even keep pushing to actually introduce a certain amount of lifting to the track. Now remember, this is slab track. Slab track, the amount of options that you have to lift your slab track or readjust the geometry on slab track is generally limited, as opposed to what you have on ballasted tracks where you can just simply use tampers. In slab tracks, you can't really do that. So we can actually keep injecting to actually lift the slab, introduce some lifting pressure, and we can monitor that lifting very precisely using laser level monitoring. Another obvious example is the use of geopolymers to fill sinkholes. Now, sinkholes is a rare, it's a rare phenomenon, especially under the railways, but it can happen. And when it happens, it can be due to a number of reasons, such as the presence of dissolution features, like the presence of a chalk layer, the collapse of a culvert, which could erode the granular material underneath the railway and create a sinkhole, water leakage in a similar fashion, and also seawater erosion could also cause sinkhole to appear on the next to the railways. What we can do, we can identify the cavity of the sinkhole, using probing and site investigation, and we can actually drill and drive our injection tubes through the cavity and start injecting the geopolymer into the cavity and start filling the cavity and also densifying all the soil that has collapsed and became loose, because the polymer will expand, remember, and it will start pushing and compacting all the soil, all the loose soil within the sinkhole cavity. The advantage in this solution is that you're going to get, almost instantaneous curing. So, you're going to get a strengthening right away. You don't have to wait for 3 days or 7 days or 28 days to get the full strength. So you almost get it within a few minutes, and you can open back to traffic. And obviously you'll be using far less quantity than conventional grouting. So because it expands, remember, so if you put 1 kilo of grout versus 1 kilo of geopolymer, the geopolymer will expand 40 times more. So you'll be using far less material. Another application is the use of geopolymers to fill voids behind tunnel lining. Now, sometimes due to water ingress, the voids can develop behind tunnel lining, which can compromise the structural integrity of the tunnel lining. What we can do, we can actually drill to these voids and inject our special type of geopolymer that would go in and fill those voids without generating any significant expansion pressure. and basically pushing all the water away, and almost reducing the sort of water, reducing the water ingress. So this is a very effective technique compared to what you get from grouting because of a number of reasons. For example, the geopolymer will solidify in matters of seconds, so you're not going to get any drips on the tracks. You're not going to contaminate the ballast as a result of that. You're not going to be affecting any running trains and trains. Sometimes trains, they can be affected by grout spillage. Sometimes it's a very clean and efficient way of doing this type of repair with geopolymer technology. Now, so far I've spoken about the use of geopolymer to fill voids, but also we can, as I said earlier, we can actually use this technology to strengthen the ground. We can inject the geopolymer directly into the ground to strengthen it. Now, as a designer, if I'm trying to build the railway trap bed, the ultimate aim for me is always to ensure that I've got sufficient thickness of trap bed design to protect my subgrade adequately. So that's the ultimate aim for any trap bed designer or even pavement engineer. So that's the ultimate aim. Now, the ugly reality is that this is not always possible, and this is due to a number of reasons. For example, you can have an undetected soft spot. Your ground investigation, you're not going to be investigating every inch of the track or every inch of your ground. You're going to be probably collecting samples every 50 meters or every 100 meters. So you might actually be missing some soft spots here and there, and therefore you're going to end up with an under design. Budget constraints sometimes can also have a big impact on your design because simply, the client may not have sufficient funding to provide a full thick design. Therefore, you're going to have to kind of make it shallower, and as a result, the design is not going to perform as it should be. Also, excavation constraints. Excavation constraints can sometimes be a deal breaker here because if you've got a nearby foundation or a nearby slope, excavating to a certain depth can compromise that foundation. Therefore, you can't really excavate that much, and you're going to have also a shallower trap bed design on a weak ground. So your design will perform poorly. What can we do? We can actually inject geopolymer directly into the subgrade, natural subgrade, and strengthen the subgrade. Now, this is very relevant with clay soils. So when you inject the geopolymer in clay soils or under the track in clay soils, what will happen is that the geopolymer will spread into the clay soils using a phenomenon called hydraulic fracturing. So you're almost going to end up with creating some sort of root-like lenses of geopolymers that looks like this, as you can see here from the image. And what these root-like lenses will do, they will basically reinforce the soil, but also add an extra confinement. And with it, you can actually substantially increase the shear strength of your soil. We've done some testing in Austria to actually understand where this is, how much we can get. And what we had a testing pit where we filled it up with very soft soil, clay soil, and we measured the stiffness of that soil before and after the injections. And before the injections, the soil modulus was around 4 MPa, so which is really low, really soft material, which could occur on the railways. That I've seen cases where this is not an uncommon case. And after following the injections, we managed to increase the soil modulus to almost 12 or 13 MPa. So that's almost a 3 times increase in the soil modulus. And obviously, as a result, you'll get as well increase in the shear strength and bearing capacity of the soil. We tend to do testing, pre and post testing on almost all of our sites when we do the treatment. So to make sure that we don't leave the site without making sure that we've addressed the problem and we've increased it to the desired targets. How can we use it? Well, one simple way of using this approach is, if you've got soft soil and your track renewal is up and you need to do a track renewal. So if you have a soft soil that has a modulus of 4 MPa, similar to what we had in the test in Austria, your track bed design, according to NetCorel standards, would require 450 ml of type 1 plus 300 ml of ballast. 300 ml ballast. Well, what we can do, we can actually come in and before doing the renewal and taking anything out, we can actually carry out the injections before that and increase the stiffness of the subgrade to a certain level. And with that, we can actually reduce the requirement for the type 1 from 450 to only 150 ml. We can even keep injecting to almost eliminate this requirement. So with that, you can actually reduce your depth of granular material by almost 66%. We can use this treatment because our equipment is really lightweight and easy to move and maneuverable and mobile. We can actually treat very discrete soft spots. So it doesn't, we don't have to carry it on, do the whole treatment for the entire length. You can actually, if you know the problematic location, we can just do a targeted approach where we treat a soft spot with a little bit extra on the sides to create a transition to it, to treat it. So we can actually apply this treatment at discrete locations. We can even use this treatment to replace sand blanket requirements. Now, if you look at network rail standards tells you that if you've got certain traffic conditions and certain ground conditions, you can actually, switch from the use of a complete 100 mil sand blanket to something called sand replacement geocomposites, which means that you don't have to excavate as much. But that requirement can only be achieved if your ground is competent enough, strong enough. So if you've got like almost firm to stiff clay, this is where you can actually apply this approach. And you can switch from sand blanket requirement to sand blanket geocomposites. Well, now with the injection technology, you can actually, if the ground is not strong enough, you can actually inject the geopolymer into the ground, make it stronger, and therefore you can switch from sand blanket, allowing you to switch from sand blanket to sand replacement geocomposites, and that hence saving you a lot of excavation and logistics and carbon footprint with this approach. Another application where this technology can be used is on embankments. Now, our embankments are built almost 100 years ago from poorly compacted materials with inadequate drainage and poor vegetation management. And as a result, you get all sorts of different types of failures related to the slope stability of the embankment, and you also get some shrink and swell behavior if you've got some shrinkable clay and high water demand trees nearby. What we can do, we can actually inject the geopolymer into the embankment shoulders to stabilize the slope. Remember when I said we can actually increase the shear strength of our soils? Well, if you do that, by default, you'll be able to increase the stability of the slopes. And we can inject it like here, as you can see here. This is from one of the examples of one of the sites that we're dealing with in Poland, where you can actually see the geopolymer being injected into the embankment shoulder to stabilize the slope of the railway embankments. We can also treat desiccated clay problems, especially if you've got an embankment that's made of like fissured type of clay that has a lot of fissures. These types of clays are generally very susceptible to shrink and swell behavior. So what will happen? Your embankment will shrink in the summer and expand in the winter. As a result, you're going to get some sort of funny degradation patterns on your track quality, where the track is very stable during the wet season, where the swelling has taken place, and in the dry season, where everything shrinks back, your track quality is degrading at a very high rate. Especially now, if you've got fissured clay, this phenomenon can be observed very, very clearly. And if you've got high water demand trees, the problem is even worse. So what we can do, we can actually inject small amount of geopolymer around where you've got the shrink and swell problem, and almost freeze the shrink and swell cycle. So we can do shrink swell treatment, and we can also do strengthening. So you will get both as a result of the injections. Now, using this technology, you will have minimum disruption to the railways, because we can work from the shoulders of the embankment. The process is very quick. It's a sustainable solution. So if you compare it to full renewal, full reconstruction, you're going to be saving a lot on the carbon footprint, and it will, by our modeling figures, we will be able to reduce track degradation from somewhere between 60 to 70%. And if you compare it to the cost of full reconstruction, we're about 40% cheaper. That's not accounting for possession costs. We can also use this technology to create transition zones. Now, as you know, especially on high-speed railway lines, you may get transition problems if you're moving from plain line built on normal subgrade or soft subgrade to a line or to a track that is being built on fixed support, almost like a fixed support, like a bridge, for example. And as a result, you get significant variation in dynamic loading, voiding, and subsequently some differential settlement and voiding. What we can do, we can actually use our technology to actually treat this type of problem. Now, before we go into that, it'll be interesting to look at what is the conventional way of treating this type of problem. Well, unfortunately, in the UK, we don't really have a standardized way on how we can treat transition problems. You may find some stuff in the continent, in your NEO-IC, that tells you how you can create transition designs. However, these designs are really not practical, or not, it's very hard to install on UK railways. And this is because they involve extensive amount of excavation. They're more applicable on the new construction side. So what we can do, we can actually inject the geopolymer in such a way that we strengthen the soil in a gradual manner to create almost like a transition zone without taking anything out, without taking the track out. Everything will be left in situ, and we can apply this technology to create a smooth transition. And we can even, design it in such a way to hit certain levels of changes that the client is after. Also, if you inject in certain layers in a certain way using certain types of geopolymer, we can actually introduce track lifting, so we can actually lift the track if we need to. This could be useful when you have tunneling taking place underneath your track or your structure. You can actually use this technique as a settlement control, so we can come in and inject and lift up structures or ballast, or trap bed to the right levels. And as I said, the injection process is very well controlled, and we can monitor it live using laser levels to ensure that we've hit the lifting levels that we're after. And this is how it looks. If you've got like a tunnel boring machine that's going through under your infrastructure, we can actually come in and start doing the injections to lift the different sections here. Also, another application of this technology is the use of geopolymers to damp or disturb the vibration transmission to nearby residential buildings. As some of us may know, that if you're building a railway line next to a residential buildings, there's a good chance that under certain conditions that you would get vibrations being transmitted to nearby residents, which could really affect the well-being of the residents and their health. So what can we do? We can actually create almost like a geopolymer barrier into the ground that would actually almost disturb the transmission of vibrations from the railway line to the nearby residents. And this is not something that we've came up in that sense, but this has been studied in a number of countries and been tested, and it has shown that you can actually reduce the vibration transmissions by up to 60%. So what you see here, the figure on the left-hand side, is a vibration measurements before and after the installation of a barrier that was done in some laboratory testing in France. You can see that. And this is because the reason why we're getting this improvement is that geopolymers have very high damping properties, so they can really damp out high levels of vibrations very efficiently and effectively. They've even done some testing as well in Canada, where they've created a 25 centimeter trench and they filled it up with a geopolymer and basically compared the levels of vibrations before and after. And you can see a significant improvement. So this is the sort of conceptual injection plan of how we would also do it without creating the excavation trench and basically injecting along the railway line to disturb the transmission, almost creating like a curtain that protects the property from these vibrations. Another application also is with shallow UTXs, or shallow under-track crossings. Now, typical under-track crossings needs to be installed about 100, almost a 1 meter below track level. And this is to ensure that the under-track crossing is well protected, and also to ensure that there's no hard spots being created at the surface. Now, if you try to move the under-track crossing to a shallower level. So instead of installing it at 1 meter deep, installing it, let's say, half a meter deep, you tend to end up creating high dynamic loading, ballast attrition, differential settlement, and track faults. So you tend to get a lot of problems. And I've seen cases where this has happened, and the consequences that you tend to get a lot of poor track quality around that location. So what we can do instead of filling the UTX with granular compacted materials, we can actually change that to geopolymers, to just purely use geopolymer, and we can actually select the right type of geopolymer that would provide the perfect stiffness, so the train wouldn't feel any change in track support. And as a result of that, we can actually design it so we can have or allow the installation of a shallow UTX. So instead of going to 100 to 1 meter below ground level, you can go up to half a meter below ground level and install the UTX with no issues. The advantage in this obviously is that you're going to save a lot on the site logistics, and there's disruption as a result of not having to dig a meter deep and compact the infill material, and you will have a perfectly running operational good track. Now, last part of this presentation is about case studies. So I've picked up a few case studies from our railway sector to take you through through some real examples. One case study is from Kentish Town. So part of the slab track in Kentish Town was deteriorating in the rapid rate due to the presence of soft underlying conditions and also poor drainage. So this is a very old slab that had those issues. And there were a lot of cracks started to develop on the slab, and along with really poor track geometry and track faults. So we were called in as part of temporary work. So what they wanted to do is to stabilize the track until they come back and remove the track and replace it with ballasted tracks. So what we've done, we've carried out our injections in pairs at 1.5 meter intervals and injected at a depth of 1.5 meter. And as we injected, we monitored the levels to ensure that we've lifted the track to the desired level. And what the client did at the time was basically they measured the track deflection before and after the injections. So before the injections, the track was vertically deflecting by almost 6.5 mil. And after the injections, the track was deflecting, was reduced or was deflecting to almost 2 mil. So that's about 70% reduction in track deflection. You can see here from the video how the track was behaving before and after the injections took place. We've also looked at track geometry recordings before and after, from the measurement train, and we've looked at different parameters in the track geometry. So we looked at twist faults, vertical tops, and dip angles. So the red curves represents the readings before the measurements, and the blue curves represents the measurements after the injections have taken place. And the dashed areas is where we've actually applied the treatment. You can see before the treatment, there was a very high values on the twist and vertical top and dip angles. And after the injections, you can see a substantial improvement in those parameters, to the point that we even eliminated the presence of dip angles altogether. Another example is from a level crossing somewhere in the northern eastern region. So the level crossing was experiencing significant levels of settlement due to the presence of peat or soft clay and peaty layers and soft clay. And also the drainage was not really adequate. As a result, they ended up with high levels of settlement up to 60 mil deviation from the track geometry, resulting in a level 2 track faults. So they needed to really do something about it. So what we've done, we've been called in as part of emergency works to actually come in and re-level to stabilize the slab and re-level it to the right level, so lift it up to the right level. So we were working to tolerances between 0 mil and minus minus 10 mil. And what we've done, we basically injected into the type 1 layer below the slab, 50 mil below the slab, and we started lifting the slab and injecting the material and lifting the slab while we're monitoring it using laser levels. But we also had a third-party surveying team also making sure that we're achieving the right levels of lifts. We looked at the lifts from two perspectives. So, lifting the track from an absolute point of view. So we looked at the center line of the track, and we also looked at the relative difference between the two tracks, or between the two rails, to ensure that we're not lifting more, one side of the rail more than the other, to avoid any sort of twist faults. And what we've done, we basically looked at track geometry recordings before the treatment and also after the treatment in subsequent months. So you can see the red line represents the track geometry response before the treatment, and you can see that this big blip is where we've got the level crossing. And after the treatment, you can see here there's a significant improvement, and and that improvement seems to be almost staying roughly around the same level for a few months after that. So it seems like we managed to lift the track, but we also improve the track geometry and improve the long-term performance. And you can see this in both upline and the downline. So both lines were experiencing similar patterns. And if you compare what happened to the track geometry before and after and how it was degrading, there was a high level of degradation over time before we interfered. And as we came and introduced our injections, the track seems to be very stable after that. And we estimated that the track geometry was improved by around 70% from degradation point of view, but also from an absolute point of view, where we just simply fixed the instantaneous track quality. And what we think this is the reason why we're getting long-term performance is that, yes, we have injected right underneath the slab to lift the slab, but because we injected 50 mil into the sub-base, basically what happened that the geopolymer created these sort of bulbs of geopolymer, and what these bulbs will do will basically increase the contact area between the slab and the ground, and also confine and compact the ground in the soil. So this is why we were ending up with long-term performance as opposed to just lifting, and performance would just go back to bad levels again. Another example is from Franduck depot, Farnham depot. The depot was experiencing significant levels of settlement due to poor infill material and water ingress. You can see the top right-hand corner picture how the track was looking like. The picture is quite amazing how bad it was, and we were commissioned to basically inject the ground and re-level the track and the depot. And you can see the picture after it. It's just, you can see the difference. There's a significant difference in how we managed to actually get the slab exactly to the right levels. Another example for embankments in Poland. So in Poland, near the central part of Poland, there was a track that was built on an embankment that was experiencing significant levels of settlement and ballast loss. This was due to soft underlying conditions and animal borrowing. As a result, we ended up with a lot of material loss, high track deflection, and even localized sinkholes started to appear under the track. And this is just a video to show how the track was deflecting when a train passed by as a result of the animal borrowing and the soft underlying conditions. Okay. So what we've been commissioned to do? Well, we've been commissioned to stabilize the entire embankment. So we carried out an extensive injection scheme, basically to treat about 50 meters of the track, and injecting it at different levels up to a depth of 4 meters. And this is just to show what sort of injections we did. So we've treated both sides of the embankments and also underneath the central line of the embankment. We treated all that, and we carried out dynamic probing before and after the injections. The red bar represents the blow count before the treatment, and the blue bars represents the blow count after the treatment. And you can see here in two locations there's a substantial improvement in probing, or in the blow count before and after, almost in some instances almost 6 times increase. And that will translate in a significant increase in shear strength and track modulus. Another example is from Vajala Bridge track lowering in Finland. So what they wanted to do some track lowering under a bridge. So you can see here the bridge, and they wanted to do some track lowering, and the track lowering was about 800 mil. So that was quite a high level of amount of, quite high levels of track lowering. So it's not something that you can just simply do. And the reason for this is that because if you excavate and lower the track by 800 mil, you may undermine the bridge foundations. And this is how the bridge foundation looked like. So what we've done, we basically carried out extensive amount of injections to basically solidify and treat all the soil underneath the foundation to a depth of 2.5 meters. You can see here with this shaded block. And this is all treated material, underneath the foundation and also on the sides, just to make sure that the soil is stable before they start carrying out the track lowering. And after we finish the work, they've carried out they would actually come and do the excavation. So as part of the design, a third-party consultancy did the work, and they've done some modeling to it to see what sort of level of improvements we did, and also to verify that the material is behaving as it's supposed to be. We've taken some core samples after the injections were carried out and before track lowering. So we've done the injections, taken some samples, tested them in the lab to make sure that we've got the strength that we need. And then after they got the desired results, they actually came in and did the excavation. So the project was executed within the time limits, and the bridge, they predicted that they were going to get some settlement, about a few millimeters of movements, but actually after the work was completed, they didn't really observe any significant settlement, so it actually performed slightly better than what we anticipated. And the final example is from Chopra tunnel. So this is a project where we've actually injected below the tunnel lining. So what the client was experiencing was they had significant amount of voiding behind the tunnel lining, to almost having voids up to 0.5 meter deep into beyond the tunnel lining. So what the client wanted us to do was basically to inject and fill these voids behind the tunnel lining, and also to fill the shafts of the tunnels. So what we've done, we've basically drilled through the tunnel lining and injected the geopolymer behind the tunnel to fill all those voids. And you can see here some pictures of the drilling and the injection of the material. But also we use a geotechnical rig out from the outside to actually drill through and get to the shafts and inject the geopolymer into the shaft and fill those shafts very effectively. And I think that concludes my presentation. Thank you all for listening, and I hope you found it interesting, and maybe it's time for some questions. Alistair?
Indeed it is. Thank you, Mohamed. That was very, very interesting. I hope everyone took something useful from that. And I know I'll say for you, Mohamed, that you're available to speak to teams if necessary to do subsequent presentations and expand on particular aspects if there are any projects you're working on. So if you've got any questions, type them in the chat box. I'm just going to whiz back up here and pull out some questions from earlier on. Eric, hi, does this technology apply with ground penetrating radar technologies to identify voids?
Yeah, so potentially you could use ground penetrating radar to identify voids. You can use also microgravity. You can use probing results to actually get this, try to understand where the voiding is and do the drilling, because that's quite important to identify the locations of these voids prior to doing the injections.
Okay, and Robert asks, when drilling in sinkholes or other types of voids, is there a maximum depth of the polymer that you can inject to?
Well, I think we can get our polymers up to, I think that the maximum we've gone is around 12 meters, I think. So 12 meter deep, you could potentially do that. So I think that's the sort of maximum depth that we can look. I think it could be stretched to 15 meters, but yeah, somewhere between that. So it's really dependent on the problem as well. So, but roughly it's somewhere between 12 and 15 meters, I think. That's the limits.
Thanks, Mohamed. Ali asks, any approximate cost comparison between resin and two likely alternatives, for example, so grout and type 1 fill per meter cube?
In terms of cost by cost, it's quite hard to give a very clear figure in terms of how much you would save or what's the sort of meter cube difference. Is pounds per meter cube. And this is because it's really dependent on the design and what you're trying to achieve. But what I can tell you is that what we tend to see from examples is that the use of this technology allows you to save in many in many prospects, in many aspects. Sorry. So if you use this technology, you'll be saving a lot on site logistics. You'll be saving a lot on time, and also on carbon footprint. So there are many savings associated with this. So it's really hard to ping a specific, comparing it meter cube by meter cube is quite hard, because it's really dependent on the type of polymer and all of that. So if you've got any examples you would like us to look at, I'm more than happy to go through it and tell you what will be our alternative, and then you'll be able to kind of get to gauge a difference in the cost savings you'll get between our solution and the alternatives.
Yeah, exactly. It's really case by case. So thanks, Mohamed. Ali follows up there. Given limited access common on railways, what sort of equipment is required when filling voids?
Well, we've got, depending on the access. So again, if you could access the embankment from, somewhere at the bottom of the embankment, if you've got a nice access to that, we don't have to get onto the track. So we can do all the injections from the sides. And this is what you've seen from the Polish example, where we treated the embankment. We didn't get it on the track at all. So we actually came from the sides. And this is really, again, if you've got access that permits you. If you don't have access that permits you, we could use our mobile unit, which is mounted on a bogie or on a trolley, and then we can get access from the track. So it's really dependent on the site, but our equipment is not that large in that sense. So we're talking about an injection gun and a pump and two barrels of material of our geopolymer. So it's not a very extensive amount of installation, and a typical gang will be around 4 people. So again, not a lot of people, so it can be done very quickly and much easier than alternative solutions.
Absolutely. Just to follow up there, we did a job some time ago on Dumbarton Castle, which was an old French prison, and this was something like 200 meters high, and people had to we had a truck at the bottom. People took our hoses up, climbed up the edge of this cliff, and we were able to inject from the bottom of this up to the top using hoses. So I think that's one of the beauties of the solution, is the lack of plant or anything needed for that. Carmen asks, is there a minimum thickness? I'm not sure I understand that. A minimum thickness, Mohamed, maybe this is in relation to...
I don't know what we're referring to here. So perhaps...
If you can clarify, Carmen, what you're referring to on that one. We'll give you time to come back. James asks, what's the lifespan of the geopolymer?
Okay, so the lifespan of the geopolymer, we've done accelerated chemical aging, accelerated testing, and fungal testing and bacterial testing, and the testing has shown that it could last a minimum of 60 years from an aging perspective. From a fatigue perspective, as I mentioned earlier in my presentation, it should last 120 to 140 years. So probably somewhere between those two figures, between 60 years and 120 years.
Yeah, hopefully that answers that for you, James. So Yu Chung, what is the effective diameter of one injection hole?
That's a very good question. So when you're injecting, it's really dependent on what you are injecting in. So if you're injecting in a granular soil, which you tend to create these sort of bulbs of geopolymer, these bulbs will have a diameter somewhere between 0.4 to 0.7 of a meter, but the influence zone of that bulb can extend almost 1.5 meters away from the center of that bulb. So quite a large zone influence. So almost 1.5 meter each side. That's the sort of influence zone you will get. When you're injecting in clay, if it's soft clay, we're talking about a radius of 2 meters, so roughly 2 to 3 meters. If it's stiff clay, it can be longer, but obviously, injecting in soft clay may not be, there may not be a good reason why you would treat soft clay, stiff clay in that sense. But yeah, so I would say for granular materials, about 1.5 meter radius. For soft clay is around 2 to 3 meters away from the injection point.
Okay. Adebayo, can geopolymer be mixed with concrete during construction?
Ooh.
I've not had that question before.
Yeah, that's an interesting one. The honest answer is I don't know. What I can tell you is our geopolymer, if you've got dry concrete and you inject next to the dry concrete, the geopolymer will have good bonding with the concrete. So it'll bond nicely. But I don't know what happens during mixing. The problem is the geopolymer will only requires few seconds for it to actually cure. And obviously the concrete will take a few days. So I'm not sure what will happen. I think we have to test it somewhere in the lab to give you an answer on this one.
Yeah, that would be a bizarre experiment. I don't think it would work.
I don't think so, but I'll be interested to see this in the lab.
Yeah. We've got an R&D department, so we'll pass that thought on at Adebayo. James asks, following on from the lifespan question, what repairs be to just inject the polymer? What repairs to be to? I'm not sure I understand what you mean there, James. What repairs be to just re-inject? Oh, right. Okay. So can we re-inject the polymer? I think after 120 years, or I think that's.
You can always come back to the same drilling position and re-drill and re-inject, and the geopolymer will just spread through inside the old polymer. So that's not a problem.
Yeah. Carmen, just following up on the earlier question. So the thickness. So as grout has a minimum of 10 mil for the example. So I don't think there's not a minimum thickness of our geopolymer material for it to be used, because it goes through veins.
I think I know where Carmen is coming from. I think the material is not like a continuous layer that has a specific thickness. What the material, you could have really any thickness you want, but it's really depending on your loading requirements. So if you want to use this material, let's say under a slab to create like a continuous sheet of polymer, obviously you can put any thickness you need, but that needs to be looked at in conjunction with the loading that you have to ensure that the geopolymer can actually take the bending and all that. So I don't know. I hope that's this is what the question was about.
Yeah, and by all means, come and get in touch. We'll come back to you if that wasn't a suitable answer. Oh, yes, it was. There we go. And then, so Robert, do you have different types of polymer for different works? And what international approvals do you have to carry out works?
Well, we do have different types of polymers. That's to answer the first part of the question, to carry out different types of work. Now, in terms of approvals, I think we've recently obtained the certificate of BBA, which we're happy to share upon request. So I think that's something that we've achieved last year. We're also applying for approvals like certification approvals from the highways and from the highway agency and the railways. So yeah. And generally with other companies called Eurotech that use our solutions around the world, they have their own approvals in those particular countries. So if you're not in the UK, Robert, or you're thinking about another country, that would be the best port of call. But drop me an email, Robert, if that's not a sufficient answer. And Adeyoke, I hope I pronounced that, silent J. Could the polymer be used for tunnels with water ingress issues? Yes, you can. You can use the polymer to inject behind tunnel linings to create almost like a layer that would reduce the water flow and the water ingress. So yes, so this is something that we can do. Yeah, and I think we have done that as well. Yes, so, and then we've got a couple more coming through. Ali, do you provide any warranty for your works and products? If so, how many years warranty would be provided? I think this is really dependent on the application. So it's really depending on the application and where we're putting the warranty vary, or whether we give warranty or not. It's really depending on the application criticality of the project. So I don't have a definite answer. It's really project by project.
Yeah, that's great. And Robert, we do have a Geobear operating in China. So if that's the area you're thinking, but there are other Eurotechs in those countries as well. So right, is this a question or right? Let's add a bow. Geopolymer concrete can be seen as a more viable solution to high energy intensive conventional Portland cement concrete. Yeah, thanks, Adabay. I think you're making a statement there, and I wouldn't agree with that too much, Mohamed, unless you've got a comment on that.
Well, the temperature, if we're referring to the high temperature of curing, is really dependent on the type of polymer. We do have polymers that do not emit high levels of temperatures. It's really dependent on that. And depending on the application. So we do have polymers that do not generate high levels of temperatures. So for sure. So I've seen that, and we can always tailor the design to account for that if the temperature, if the curing temperature is an issue. So
yeah, I think the Geopolymer concrete is a slightly different product.
Yes, so that's also another thing as well to keep in mind. So Geopolymer concrete is not the same as geopolymer. So Geopolymer concrete is something completely different. So I think it's worth to have a look at that, because they're not exactly the same.
No. Have you the need? This is from Kieran. Have you need to test the product regarding fire properties? Might not be an issue as it's ground treatment, but.
So we've tested the geopolymer from a auto ignition point of view, and our geopolymers have an auto ignition temperature of around 400 Celsius degrees. So that's the answer to your question, I guess.
Yeah. So the testing has been in place. And Robert, Malaysia and Singapore. Okay, Eurotech in that case. If you Google Eurotech in those areas, Robert, hopefully they can help. But looks like that's all the questions, Mohamed. So really appreciate your presentation and answering all those. Hopefully we Mohamed answered those effectively. And if you've got any other questions, though, I'll send a recording of this to you on an email probably Monday morning. So reply to that email and I'll try and help. And if you've got any other general questions or projects or schemes on the railway, we are open to looking at them. And we're in fact always running trials as well. So if you think there's an application or a suitable use, then we'll have a look at it. But thanks everyone. Thanks, Mohamed. Everyone seems to appreciate that. All the best. Have a good weekend, and look out for future webinars. There's a good one actually on the 1st of April, which again Mohamed's running, and that's looking at geopolymer use on actual structures, more like commercial buildings, slab lifting in commercial buildings, ground improvement for commercial buildings as well. So you may find that interesting, but you can sign up on our website. But okay, thanks for now. Cheers, Mohamed. Thank you.